The next one I want to cover is a line network based mesh again. And this one will try to replicate the under magnitude pavilion. It's an art installation by the very many. So the workflow we'll be covering now is to create a line network and then wrap a mesh geometry around that line network, which can give us clean strips. I will cover this in a couple of ways, giving us a triangular mesh and a quad mesh, and how to really achieve a line network that can give us this dense pattern, because we don't want to create this line network manually. So let's see how to go about it. I have this example script which I will be sharing with you after the end of this session. There are two kinds of curves that I have. There's one which has been created using anemone and loop. There's a definition that was created to ensure that these lines grow without intersecting with the other curve. And there is another one which was made manually like this. So let me explain the workflow for creating this line network through anemone first. Before I do that, let me just show you how it will grow. So when we use a definition like this, and if I just start running it, it will grow into a network, and I can increase the number of lines by just moving a slider. And the criteria that we have assigned for this particular network is that each node will only have 3 lines converging to it. 3 or less, not more than that. And the second criteria is that the distance between any of these lines on the screen will be greater than twice the radius of the pipe that we are going to be wrapping this with. So if you're going to wrap this with a pipe, and if you're going to wrap this with a pipe, we need to ensure that the distance between the two is greater than their individual radius, so that it doesn't intersect. All right, so let's see how to do this. Before I start with this, are you guys familiar with anemone or looping in Grasshopper? Could you just give me a yes or a no on the chats? Because then I will see whether I need to explain it or not from basics. I'm just going to take 10 minutes to explain it. Anemone is a component in Grasshopper that is really powerful in creating loops. Now, loops is one of the most fundamental concepts in computation. It allows you to repeat a certain task multiple times. And in this case, we are going to define a function which is going to be a growth function for line network. And we are going to ensure that it doesn't. And we are going to ensure that that function gets repeated until certain conditions are met. An example of this I will like to show you using a point and something called a random walker. So imagine we have a point over here. Now I'm going to write a small definition which will allow this point to move randomly and grow from this origin point to some other point, and that movement will then be joined with a line. I'm going to write a small piece of code which will be repeated multiple times. So that's the point. And the command is going to be that take this point, move it. Now, as soon as I use the move command, and let me switch on the bifocals. As soon as we start the move command, it has a basic motion of positive 10z, which is the default value. Now I want to assign a function where I want to assign a random vector in any direction. This is going away from this point. Let me do it with random. And I will create a vector x, y, z. And this component gives us random values. So I will add a slider of 50 to the seed, and I will add a range of construct domain which defines the range of the numerical range for the random number. I'm going to make it between -1 and 1. So that's -1, and this is 1. This goes over here, and the number of random points I want is 1. So that's over here. I'll copy the same thing again and again. Notice that all these randoms have the same seed value, so it will give us the same number. So we need to change the seed. All I'm going to do is I'm going to have one slider. For the rest of them, I'm going to add a number. Let me add 6 to this one. Let me add 17 to this one. That's the seed. So that's X, Y, Z. That's giving me a random vector value. So that is going to go over here for motion. Now just to visualize what happens, if I keep moving this, you'll see that this point moves in random directions. Now what I want to do is at every step, that means starting from 0, it will take this movement, go over here. Then for the next number, whatever is the random vector, it will move in that direction, then in the other direction, and so on. Just keep growing. So this is the basic setup. Now, how we introduce loop in this case is to take this point, we go to Anemone, and Anemone is something, is a plugin that we have provided in the plugin folder. It's a Grasshopper assembly file, which you can install by going to File, Special Folder, Components folder, and just paste it over here. You will see Anemone on my component folder list. Should be somewhere over here. Yes, it's over here. Remember to unblock it. Go to Properties and unblock it if you have that option, and apply and close. And when you restart it, you will get this. It's a neat little plugin. You don't have many options. The main options that you need to look at are loop start and loop end. The way this works is you have the number of repetitions over here, which defines the number of times you want or number of loops you want in this particular definition. So I'm going to add this. Now, the way this works is this is the start of the loop. It will take a start input, which is going to come into data. Now, if you zoom in over here, you'll see that you can add more data. But for now, we only need a point, because we need a point and it needs to move to a specific location, and then that's going to be the output for the next loop. So our input goes over here. It travels through and comes out over here. This point will go into the geometry. And then this is the loop end. So at the end of the first loop, the geometry will give us a point. And this point will go into this data. This data will again feed the data over here for the next loop. And it will keep doing the same thing till we reach the number of iterations mentioned over here. Now, to enable this, we need to connect the loop start with loop end. So these two arrows need to be connected. And once you connect this, it will no longer be orange. It should be white. You have some additional commands over here. You have something called counter. The counter keeps a track of how many loops have occurred. So this could help us replace this number slider over here. So I'll take this counter, put this over here. So at loop, if you set the loop to 10, it will go to loop number 1, 2, 3, 4, all the way till 10. So this counter will change from 0, 1, 2, 3, so on. And every step will give us a different random number. So that's giving us a different seed value. And there's an optional command if you want to give a condition to exit the loop before it finishes the number of steps, you can do that. But currently we don't have any such condition, so let's just go with it. Now, because it's going in a loop, it will start, give us the position after the point is moved, and then that will feed back and give us the next point, but it will not record all the data. We want to record all the data. So we want to record the first step, second step, and so on. So if you right click and if you press record data, it will record everything for us. So let's trigger this. Let's set this to 10. And you see automatically it has created this movement. Let me increase this to 100. And it created these random points on the screen. Let me start that again. Yeah. And now all these points, I can just flatten it. I can take it over here into a point component, flatten this, and create a poly line. So this is a very basic random walker where you're just assigning random directions for it to move. All right, I hope this is clear and it gives you a brief overview of what anemone is and how it's used. So let's try and apply that to create that line network that we spoke of. To create that line network, I'm firstly going to start with a point at the origin and start with a line SDL. So that's the start. Direction, I'm going to choose a random vector. I'm going to make it a floating point vector. So your floating point slider. So that's the direction, and the length would be anything. I am going to set this at 12 at the moment. Now this number is important because we want the line network to grow, I'm going to use this as the guiding number. I will ensure that either the subsequent lines are of the same length or they can be a fraction of this particular length. Now that depends on the kind of output you want. So we have this line. Now we'll also bring in the loop start and loop end. I'm going to set this to 10, bring it to 0, the number of repetitions to be 0. We'll use a button for trigger and the data. Keep this together. We'll also use a loop end. Now when I only connect the two but I don't give an output over here, it will still give me an error. So we need to ensure that we are feeding it a data over here. Another thing to keep in mind is that whatever data you give as an input, your output should be the same data type. You can't give in a curve and give an output of a number, because that data has to feed back over here. And if you don't have the same data type, your algorithm might fail. I'm just going to rename it so I remember what kind of data needs to go over here. Okay, now this curve will come out and I need to do something to it. So this particular line has this as a start point, that as the end point. I'm going to take this endpoint and I'm going to branch 3 lines out of here. 1, 2, and 3. To do that, you're going to take a perp frame command, perpendicular frame, on this curve, and we'll create it at a parameter of 1.0. 1.0 parameter, if a curve is reparameterized, it means that it's going to take the endpoint. Now, once we have this frame, we can create a polygon. I'm trying to create a triangle over here. I don't care about the radius at the moment, but I need it to have 3 segments. Okay, once we have this, I'm going to use something called stellate. So if you go to Weaverbird transform, there's an option called stellate. This takes mesh or polyline, and if this is our polyline, it will try to create an extruded mesh geometry out of it in this manner, which will be a 3-sided pyramid. If we have a square, it will create a 4-sided pyramid. That's how it works. So this is the polyline. Actually, I'll just convert this polygon into a simple mesh. So make it a boundary surface and a simple mesh. Just doing it so that we can visualize it. No other reason. Now with stellate, now that I have these 3 faces, triangular faces, I want to extract the center point of these 3 faces, and that center point and the direction from this point to the center point will give me a direction to grow those 3 lines. And a factor that controls that angle is the distance of this tip from this point. So that distance can be controlled over here. By default, it's set at 5. If you use a slider and set that to perhaps 3, you can get something like this. Now with this mesh, we need to identify the center point of these faces. For that, I'm going to use face normals. So that's the mesh, that's the center. And then I'm going to create vector to point. So this frame will give us the starting point for the vector, which is over here. And the face normals will give us the center points of all these faces. So the starting point, and actually, I don't even need to do that. I already have the normals. So if you see the normals, these are face normals. So vector display. I have the anchor points, I have the vectors. I already have the 3 vectors over here. Like this. So I don't need to. Okay, wait. I'm not trying to create a vector. This vector is normal to the face, but it doesn't really meet over here. So yeah, sorry. I'll have to create that vector. So these are the center points. These are the vector points. Yeah. That's how it will grow. Now, like I mentioned earlier, I only want 2 points coming out of this. So out of the 3 vectors, I need to choose 2. And that's a tricky choice, and I'll come to that in a bit. Suppose I have these 3 vectors. I'm going to do list item, and straight away take up the first 2. So I'm just going to use an input of 0 and 1. Use multi-line data and use it as an index. So these are the 2 vectors. And I can create a line SDL. That's the direction, and the length needs to be a number, and that number would be coming from here. So I will take this length, use it over here, use that over there. Now this will lead to a simple recursion, which is not helpful for us, but let me show you step by step why it's not helpful. I'm going to hide everything else. And set this to record data. And let me start growing this. Straight away, you can see that there is some problem. Now that's happening because right after step number 1, let me go back. Step number 1 is taking an input of a single curve and giving us an output of 2 curves. Now the 2 lines come over here. In the next iteration, step number 1, we have 2 lines coming in over here that were created, these 2. They go over here, you create perpendicular frames, everything fine so far. You create polygons, create edge surfaces, outward mesh. In this manner, everything good so far. You get the points. And this is where the problem arises. This is a branched list and this is a flattened list, whereas you want to divide these 2 points into 2 separate branches so that this point corresponds to the 3 center points of this list, and same for the other one. Let me just graft this over here and graft this over here. I will play it again. It kind of works. It kind of grows it, but you'll realize after some time that these lines start intersecting. They're coming close to each other, and this is something that we want to avoid. I mean, you can keep growing this, but it will not conform to the restrictions that we had set. All right, so the approach towards that would be to take all the lines that we're getting. Suppose in the first iteration, we're getting these 2 lines. We'll take this line, we'll take the initial line as well, and we will compile them in a separate list. And to compile that list, what I'll do is at every step, whatever lines I'm getting, I will put that in this D2 in a merge component. And the lines that I'm getting from the start over here, I'm going to put that into the first. I'm going to add this. I will flatten this and flatten this. I want to create a flat list. Let's start. So what I'm doing now is that every step, at every loop, whatever main curves I have, plus whatever is the new curves that I've identified as growth, will all compile into a single list in the correct order. And they will be fed back over there. So I'll keep recording all that. I won't have to use the record over here, but this is going to be that recorded list of lines. Also, what I will do is that every time the criteria to figure out which line to take up, sorry, I think it's zoomed in too much. The criteria to decide which vector to extract from these 3 would depend on whether the line created by that vector is at a significant distance from all the remaining lines or not. In order to do that, firstly, I'll replace something over here. Rather than using the D1, I'll use list item. So I've recorded all the lines over here, but let's say in this recording, this is the first line, that's the second line, that's the third line. So in the next iteration, I'm just going to take this line and I'm going to grow this. So at loop number 2, what will happen is that I'll have these 3 and these 2 lines. Then in the third iteration, I will take this line because in the initial list, this line is the third line. And then I'll grow this one. And then the fourth iteration, because this was the fourth line, I will grow this one. So I'll do it step by step. We have all the lines recorded over here. That comes out as a list over here. And I can use the counter to give me a list item. And now this will replace the line over here. Let's see if this works. Yes. It's going in a step-by-step format. That's fine. But we haven't given the distance parameter yet. Now the distance parameter will come into play somewhere over here, where we say that okay, these are the lines that are created. Sorry. These are the 3 vectors that we get for each of the curves. Now, from each of these curves, vectors, we create 3 lines. Here is the start point of each of those lines. This is the direction, and that's the number. Now we want to see whether these 3 lines obey the distance parameter from all the other lines on the screen. And the other lines on the screen are these. Now, when we are trying to assess these 3 lines, these 3 will obviously be closer to the line it originated from. So in order to test its proximity, we have to firstly remove this line from the list of lines before assessing. So we'll take the list of lines which are coming from here, and we are going to use the same index that is used to isolate that particular line to cull that line from this list. So we take the same index, we cull it. So now we don't have that line which is used to grow those 3 lines. Now that's the line. So these are the lines you want to test against, and these are the 3 lines you want to test for. Now what we are going to test is proximity. We're going to see the curve proximity for all these 3 curves. So these 3 curves, because you want to test them individually, we'll have to graph this. This is curve A, this is curve B. Now what we are concerned with is the distance. And the parameter we're going to use for distance is a radius, which I'm going to set over here. So this is the line length. And this one is the radius of the geometry I'm going to wrap around the curves. I'm going to set this to 4 for now. We'll take this all the way over here, and I'm just going to hide the wire display so that it doesn't intrude. Now, distance. What I need to check if any of these distances is less than, let's say, 2.1 times of it. 2.1 times because, like I mentioned, it needs to be greater than twice the radius. Now it can be 2.1, 2.5, that's completely up to you. Let me keep it at 2.5, but it needs to be greater than 2 to avoid intersection. And we will get a list of trues and false. Now, how do you make sense of all this and get one false, true or false statement out of this? we can convert this into number. Converting true and false into a number will give us zeros and ones. And we can do mass addition. So a mass multiplication of the first branch, because all of them are 0. All these zeros will multiply with each other and give us a value of 0. That means for the first line, the answer is false. That is, it's not it's not like its distance from any of the lines is not less than 2.5 times of the radius. So I'm going to use mass multiplication. Extend this, and this result is going to be used to dispatch. And what we are going to dispatch are these lines. So we've got these curves, these lines. Actually, we'll dispatch the vectors. Take the vector, we'll graft it, remember, because this is a grafted list. And we are looking for the false data. So in this case, all 3 lines are compliant. So they are not intruding the other, or they are more than 2.5 times of the radius apart from other lines. So we can take all these vectors, flatten this, and now these vectors can go over here. So that's the check for us. Okay, sorry, this is not a start point. That will go over here. So now out of these 3 vectors, we can choose any 2. We'll take the first 2, and that's how we'll keep growing it. So that's a check. But one of the issues in this method is that because we start with 0, and right at the beginning, if we start and we cull the first line, then there are no other lines to test the proximity with. So I'm just going to add one additional condition over here. And that condition is going to be an if statement. The statement mentions that if x equals 1, then you go with, x equals 0, you go with 0, or you go with 1. Now x in this case would be the counter. When for the first loop, the counter value is 0, whereas for the subsequent loops is going to be more than 0. That is not equal to 0. So it will give us the result 0 at the moment because the loop is set to 0. And now we are going to use a stream gate, a stream filter. I always get confused between the two. A stream filter. Stream filter works in a way where you've got one output, which is these vectors, like this, and the other output, which is right at the beginning, where we got all the 3 vectors over here. So if it's the first loop, x will be 0. If x is 0, it will give out an answer of 0, and it will not go through this proximity test, and it will just bypass this test and just give us the 3 vectors. And we know that in the first iteration, all 3 vectors are going to be away from each other. They are not intruding. And this logic will pass on further. And hopefully this should now give us the output that we want is D1, because that's the compiled list. Keep growing it. And if I edit this and make this 100, it's giving us some error over here. Let's see why is that happening. Mass multiplication. That's going to be a dispatch pattern. Okay, so probably mass multiplication is not the right approach, because even if one of them is 0, all the answers will be 0. So we need to not look at mass multiplication, we need to look at mass addition, because anything you multiply with 0 will give you a 0 answer. Yeah. Sorry about that. Let's try it again. Again, there seems to be an error. Okay. I need to reset it. All right, let me go to 1, reset this. There's no value inherited. Okay, this needs to go over here, and these vectors need to come over here. Sorry. And now I believe it will grow. So you can see how we have all these lines, and just by looking at it, none of them seem to be very close to the other. And because we're working with lines, I can just keep editing this. I can make this really large and make it 250. But I will probably stop somewhere earlier, because when we wrap a geometry around it, especially a mesh, that's going to be really heavy. I don't want to make this thing really heavy. So I'll reduce this to 50 at the moment. And trigger it again. Let's just work with this line network for now. So I'm going to take this, hide this, and just so that we are safe, I'm going to add a data dam between the two. So these are the curves. The next step when we have this line network would be, if you look at this, it's still not, it's not tense enough if you look at it. So we can use Kangaroo to really make a really tense line network out of this. We have this line network, and what we need to isolate over here are the endpoints. So we'll take the endpoints of all the lines, put them together in a point component, and we can again use sort duplicate points. And because we're trying to isolate these endpoints, we know that they will only occur once in this list of unique points. So we can prune the tree to extract the minimum, the maximum. Sorry, can't set it to 0. The list needs to have at least one element. Yeah. And we can use this index with the list item to get the endpoints. The reason I want the endpoints is so that we can make these the anchor points, and then we can give all the lines some spring force to control it. Now, straight away I see that there's still some issue, and it's not identifying these endpoints for some reason. Okay, all of them are identified except this one. Let's see. Okay, I think it works now. So we had some null elements in that list which were cleaned using the tree, and that helped. Now I'm going to anchor these points. I'm going to flatten this. So that's one goal. The next goal would be to take these lines, give it a length parameter. And I'm going to give it a target length of half its size. These two, and we bring down kangaroo solver. We use a button to reset and a Boolean toggle. And extract the lines. Now, as soon as I input this, we have a bunch of nulls and then we have lines. I'm just going to clean the tree. Remove all the nulls, and that's the clean line. You can instantly see the difference between this and this. This is trying to stretch everything and make it really tense. So already you have a line network which is trying to pull everything apart. It's anchored at the edges and wrap a geometry around it. I'll be covering two methods of how you can wrap a geometry. One which is completely simple and one which I used to use before this new method came along. So I'll do the easier one first, and that is the use of multi-pipe in sub D. Ever since this component has become part of Grasshopper, it has just made this workflow so much easier. So the way it works is that you give it a curve input, you define the node size, which is the radius. I'm going to use size 4 because that's the size I used while defining the loop. And that's the sub D model that I have. Now, don't confuse sub D for a mesh model. They are two separate things. But once you have a sub D pipe, you can convert the sub D into a mesh. So you can take this component over here, mesh from sub D. You can give it a sub D and choose the density. The density parameter will refine the mesh further. So currently it's set to 2. If you make it 3, it just refines it. But for our purpose, currently 2 should be fine. And that's up to your discretion and depending on the size of the geometry or the physical application of it. Now, once you have this, you may choose to just take this and proceed with this, or what I like to do as an additional step is to anchor the edge points and relax this model further, just so that all these edges, they are not like over here. If you see, this edge seems to be a bit at an angle, at a right angle. It doesn't seem to be flowing. So to get that, what we can do is a simple step where we take this mesh, we just isolate the naked vertices, which are these points, and anchor it. That's step number one. The other goal would be the edge lengths. I'm going to use a factor of 0.5. That's the anchor, that's the edge length, and then we merge them together. What else? Because we're working with mesh, we need the show component. Pull this down. This goes over here. So you've got the anchor and show. All these need to be flattened into a single list. Take the goals. It's a Boolean toggle. Set this to false right at the beginning. And then use a button. Okay, so we have the naked points. Oh, all right. So as soon as we isolated the naked points, we can see that it has taken up all these internal points as well. So we need to clean this mesh before we can use it. So we take this mesh, join and weld. That's what we have. Yeah, now it should work. So as we do this, the geometry itself starts smoothening in all directions, and the angles that were more orthogonal starts becoming more fluidic. But at the same time, what we are missing is the roundedness of those pipes. Because if you notice over here, we end up with these flat bits. So this is where we can use the pressure goal to inflate this. Now the way that we can do that is to go to kangaroo, goal mesh, pressure, use that. And like I explained yesterday, we're going to use pressure with a very small value. I'm going to set it to something really small at the moment. The thing with using pressure is that sometimes if the value is too high, your mesh will expand and just burst. And all that will happen so quickly that you won't even see in the solver, and you'll be wondering as to why nothing's happening. Okay, so at 0.012, there's no change, no noticeable change. Let's increase this slightly. All right, so it's almost there. It's all rounded. There you go. So that's one method of creating the mesh. And because we have used quad mesh, we can use the same technique where we can go to kangaroo, main, and go to mesh, use the mesh direction to sort it. Before I do that, let me just put a data dam over here. This ensures that if the solver is running, every consecutive iteration is not going through the next steps. That can significantly slow down your computer, almost crash it. Now we have sorted this mesh and we'll use the mesh stripper. I will get the color wheel out. Use the list length. And mesh colors. Graph these two. Okay, so I'm using the wrong input over here. I need to use this. Yeah. So now what you have are all these strips. And these strips are really helpful because if you notice the under magnitude pavilion, let me just, or the installation. You can see how each one of these strips are circular, and that's what we have in our mesh. Now, once we have these strips, then it's about figuring out the geometry, the joinery condition, or how to figure out the junction. That's something that we'll be covering when we do the fabrication aspect of it.